Thank you for the introduction. Can you hear me? Hello,
Yes,
can you hear
yes,
me?
yes,
Okay,
yeah.
great. So, okay, let me start. So, good evening, everyone. My name is Sunghyun, and thank you for coming to the talk. And the title of my talk today is Constructing Radiance Fields in Low Light Environments. So, sorry. Okay, then, yeah. So radius fields have become a powerful tool for 3D scene reconstruction, and techniques like neural radiance fields, planar cells, and 3D Gaussian splitting, and so on have shown really impressive results recently, and a tremendous number of papers have been presented for the past few years. But these approaches actually, these radiance field construction approaches assume high quality input images, but in reality, various degradations can happen. For example, especially in low light situations, images often suffer from noise due to high ISO setting and also blur due to low exposure. And these degraded images may significantly degrade the quality of radiance field reconstruction too. So in this talk, I'm going to introduce some of the recent research to handle such degraded images in radiance field reconstruction. And I'm first going to introduce some recent research for radiance field construction from noise images. And then I will introduce approaches that consider blur and noise too. And in this talk, I'll focus more on the second part, which includes our recent results, Deep Blur RF, which was presented at CVPR this year. Okay. So, okay, let's first delve into the approaches to handling noise images for radiance field reconstruction. So to handle noise images captured in low light conditions, Millen et al. Presented RONORF at CVPR 2022, and as the title of this paper suggests, RONORF aims at NERF reconstruction from high dynamic range for high dynamic range novel distances from noise raw images captured in low light conditions. So to better understand the proposed method, we first can see, actually this figure illustrates the key idea of RONORF. So here, when you capture an image, we first capture the image in the raw space, camera raw space, and this raw data is processed by the camera ISP. I'm sorry, ISP, and we have an sRGB image. And basically, when you construct the radiance field, we actually capture multiple images, so we have multiple sRGB images in this stage. And then using these sRGB images, which are actually low dynamic range images, we use them to train NERF, and then we render novel views. And these novel view images are low dynamic range images. So this is the conventional NERF pipeline. And the proposed pipeline in this paper is shown on the bottom here. Let me just clear this. So instead of using sRGB images when reconstructing NERF, the proposed system uses raw data as is. So the proposed system uses these raw images and directly train RONORF using raw images, and then using this trained NERF, we can render HDR images in the raw space, camera raw space. And here, why this is called HDR views is because raw images usually have like a more larger dynamic ranges than sRGB images, because raw images have usually raw data are usually represented in 10 or 12 bits or sometimes 16 bits. And on the other hand, sRGB images in JPEG, they are represented using 8 bits. So basically, raw data uses more bits, and so because of that, raw images have larger dynamic ranges. And then after rendering HDR views in raw space, we can apply camera ISP as a post-processing step, and then we can obtain this sRGB image. And actually, so when you in the conventional NORF pipeline, here in this ISP step, we apply, for example, image denoising to each image. So as this image denoising uses the information only from a single image, the performance of this denoising is pretty limited. So because of that, even if the ISP applies the image denoising, the post-processed sRGB images may have remaining noise and may lose some high frequency details. So because of that, even if we train NORF and we render novel views, these novel images have low qualities. So instead of this, in this raw NORF pipeline, we just directly use the raw data, and in this raw data, as we average complementary information from multiple views, we can naturally suppress noise in the raw data. And also, as we use multiple images here, when you're averaging, when you train raw NORF, we can more effectively suppress noise compared to single image denoising. So here it's like we are applying multi-frame image denoising. So we can more effectively remove noise, and then we can render novel views. So as a result, we can render a higher quality images in this as a result of this process. So let me show you some examples here. So these are on the left, we have noise input images, and these results are actually single image denoise. These images are the results of single image denoising and conventional NORF pipeline. So as you can see here, the novel view images are rendered from this pipeline still have remaining noise, and some of the high frequency details are lost. And these results these results are produced by applying video denoising and NORF. And as video denoising uses multiple input noise images, it can actually achieve higher quality image denoising results, but still this process cannot sufficiently suppress image noise, so the rendering results still have some remaining noise. In contrast, this one is the result of the proposed system, and as you can see here, the rendering results have really high quality details and minimal noise. And more than that, actually this one is designed to produce HDR images. So first, let me show you the denoising results here. So as you can see here, using this Runoff process, we can render really clean novel views. And also, we can this Runoff also supports high high dynamic range images, so that we can actually adjust the exposure of the image later. So as you can see here, we can dynamically change the exposure of the rendering result like this. And there are a couple of other works that share similar ideas to Ronorth. Another one is NAN, which was presented at CVPR 2022. And this is actually for image denoising instead of NURF. So basically, when you capture an image in a real low light conditions, due to the small amount of light, we have to use really extremely high ISO values. So because of that, noises are severely amplified, and then we get this kind of really noisy images. So on the right, we have the result of NAN, noise aware NURF for burst denoising. So this proposed method is designed for burst imaging. So burst imaging here means a technique that captures multiple images. And the main challenge in burst imaging is, so the goal of the burst imaging is to capture, multiple images and to aggregate information from those multiple noisy images to obtain a single high quality denoising result. Okay. So, and the main challenge in the burst imaging is how to robustly align the input noisy burst images. And to tackle this challenge, NIN uses IBR-lab, which is presented at CVPR 2021, to find correspondences across different views. And IBR-lab is actually a feed-forward network for feed-forward radiance field reconstruction. Okay, so we have the proposed pipeline is like this. So here we have n input images, and these input images are captured in low light conditions, so they may have significant amount of noise. And then we extract features from these input images, and then using the features, we perform IBR-lab to find correspondences between the input images. So IBR, and then using the found correspondences, it aggregates information from different views and averages them to compute the denoising result. And and there is another work that is pretty similar to HDR NURF, raw NURF, and this one is called HDR NURF, which was presented at CVPR 22. And this one is designed for also high dynamic range neural radiance fields. And so it also takes multiple low dynamic range images as input, and it reconstructs radiance fields of large dynamic range, and so that we can render novel views of high dynamic range. Okay, but this one is not designed for like a denoising or for handling low light conditions. And let me just skip this part. And similar ideas have been also used for Gaussian splatting too. So nowadays, Gaussian splatting, 3D Gaussian splatting is more popular than NURF. So similar ideas have been also adapted for Gaussian splatting. And one example is HDR Gaussian splatting here. So the basic idea is pretty similar. but they used the similar idea to the Gaussian splitting. Let me just skip this part. And let's move on to the second part, radiance field from blur images. So the task of radiance field reconstruction from blurry images is like this. So we have blurry training views like this, and we reconstruct the radiance field using these blurry training views, and somehow we remove blur and we reconstruct a sharp radiance field, and then so that we can render sharp novel views from this radiance field. Okay, so this is the goal of the radiance field reconstruction from blurry images. So to solve this problem, deep learner was first proposed at CVPR 2022. And this diagram is from the paper of deep learner. And this figure actually describes the overall pipeline of deep learner, but personally, I don't think this diagram is really effective in conveying the key idea of deep learner, so I prepared some other figures. Okay, so let me explain the key idea of deep learner this way. So actually, this figure describes how image is captured in the 3D real world. Okay, so we have a 3D target scene, and we have 3D object here, and we have a camera. And when you take an image of this 3D object, the captured image is captured like this. So there is a center of projection or center of camera, and we can project a ray. We can cast a ray like this, and this from the center of projection, and then there is an intersection. So this is basically image plane. And we can find the intersection here between the ray and the image plane, and the pixel value at this intersection is determined by the pixel value from the 3D object. So this describes the basic image acquisition process. Okay, so NERF models radiance field based on this 3D model, image acquisition model. So here on the right we have another figure that describes how the NERF models radiance field. So here we have a virtual camera, and we have 3D information, and this 3D information is stored in this MLP. And this 3D information corresponds to the radiance field. And at this using this virtual camera, we can render an image like this by sampling by casting rays like this from the center of projection. And along this ray, we sample multiple colors, and then we aggregate them to determine the pixel value at a particular pixel on this rendered image. And so NERF trains this MLP by rendering this image, and by comparing the rendered image against the input image. And so basically we compute the difference between the rendered image and the input image, and then we backpropagate the gradient back to the MLP, and we update the parameters of the MLP from using multiple input images. And once the MLP is trained, we can render novel views from for other viewpoints. So this is basically how the NERF models radiance fields. Then what about when we have blurry images? So this figure describes how a blurred image is captured. in the real world. So basically, when there is a camera motion or camera shakes, the center of projection of the camera moves like this during the exposure time. So because of that, for each pixel position, we have multiple rays coming from different positions of like this. So we have multiple rays and we have the colors from these multiple rays are averaged together, and a single pixel value is determined on this blurry image. So because all these pixel values at different locations are aggregated together, we have this blurry image. Okay, and deep blue nerve models deep blue nerve models camera shape based on this model. So again, we have an MLP here, and this MLP models sharp radiance field or sharp 3D information. And we have another MLP, and this MLP models per pixel ray jittering, or it describes camera motion during the exposure time. Okay. So for each pixel, we so to render a blurred image in this model, we basically sample multiple rays per pixel. For example, we may sample like 5 rays per pixel, and this MLP provides different offsets, the offset of each ray at each pixel. And by averaging pixel values from multiple rays, we can render blurred images like this. And then we can compare the rendered image and the input image, and we can compute the difference, and you can backpropagate the difference to train both of this MLP and this MLP. Okay, so these two MLPs are trained in an end-to-end fashion. And once these two MLPs are trained, then we can simply use this MLP to render sharp novel views. Okay. And after deep blue nerve, a number of different variants of deep blue nerve have been proposed. For example, so in the original framework of deep blue nerve, we have 2 different MLPs. And for this one, we may use, for example, different 3D representation instead of MLPs. So we may use a voxel grid or 3D Gaussian splitting. So, according to different representations, there have been presented different papers like this. And also, a number of different papers have been also presented to propose different models or different constraints or different priors for this camera motion modeling. So the key idea, even though there have been a number of different papers have been published for the past a few years, the key idea here is basically very similar. Okay. And actually, so these approaches share very similar limitations because they share the similar key idea. And actually, this deep blue nerve, the key idea of deep blue nerve is actually very similar to the traditional blur model-based deep learning approach. So here on the right, this figure describes the traditional blur model-based traditional blur model for image deep learning. So we have a blurred image, and this blurred image is modeled as a combination of as the convolution operation between the blur corner and the latent sharp image. And this blur corner describes the camera shake. Okay, and so this blur corner actually this blur corner corresponds to this MLP, and this latent sharp image corresponds to this MLP that describes this sharp radiance field, and this convolution operation corresponds to multiple ray sampling in this Dibler-Nerf framework. Okay, and in fact, there are actually many traditional multi-frame deep learning approaches based on this traditional convolution-based convolution-based blur model. Okay, and these approaches take multiple blurred images of the same scene like this, and then they simultaneously estimate the blur kernel for each input blurred image and the latent sharp image by aggregating information from these multiple input blurred images. Okay. And the problem is that the traditional blur model-based multi-frame image deep learning approaches have many limitations, many technical limitations, and also similarly, Dibler-Nerf and each variant share really similar limitations to with these traditional blur model-based deep learning approaches. First, the Dibler-Nerf and each variant they rely on linear blur models, which means they perform simple averaging of multiple rays per pixel. So because of that, they cannot handle nonlinear outliers and Sunghyun noise that cannot be described by linear blur models. For example, in this example, we have a training view here, and this light streak is not modeled by this light streak cannot be modeled by simple ray averaging. So because of that, when you have these light streaks, Dibler-Nerf and BACS, they cannot reconstruct the sharp radiance field, and so if we render novel views, then the novel view images may have remaining artifacts like this. And also, when you have severe noise in input images, such severe noises cannot be modeled effectively by linear blur models. So previous Dibler-Nerf-based approaches cannot reconstruct sharp radiance fields, and if we render novel views, and the novel view images may have remaining noise like these. Okay, and here BACS is basically this one is based on Gaussian splitting, but basically the key idea is very similar to Dibler-Nerf. And the second limitation is that these Dibler-Nerf and each variant, they do not really use any priors on sharp images, but they rely solely on complementary information from different views to reconstruct sharp radiance fields. So because of that, they may fail when all input views exhibit similar blur directions. For example, here we have multiple input blurred images, and these input blurred images actually have the same blur, similar blur. Okay, and because of that, if we apply Dibler-Nerf or BACS, then these methods fail to reconstruct sharp radiance fields because they register no complementary information between in these images. So if we render novel views, then the rendered novel images still have remaining blur like this. Okay. And the third limitation is that they are really slow in the training time. So in the training time, they need to sample multiple rays per pixel. Okay, so if for example, if for example here n is 4, then it means that to render a single rendered image, single blurred image, we need to sample 4 rays for each pixel, and it means that the rendering time takes the rendering time is 4 times slower than the rendering time of the conventional nerf. So it means, and as a result, the total training time is 4 times slower than uh, 4 times longer than the training time of the conventional nerf. And usually we need more than 4, basically, especially when you have large blur. So um, it becomes significantly slower when as the number of layers increases. On the other hand, in image deep learning, um, recently recent image deep learning approaches, they no longer use the traditional convolution-based blur models. Instead, they adopt feed-forward deep neural networks that directly predict deblurred images from input blurred images. So thanks to that, and this kind of deep neural network-based image deep learning approaches have been extensively studied for several years now, and they have been shown very effective in handling severe noise and nonlinear outliers as well. And also, as they use feed-forward networks, they are really computationally efficient. So then the most naive idea to reconstruct the radiance field from blurred images would be a naive combination of DNN-based image deblurring and radiance field reconstruction. Specifically, we may construct a pipeline like this. So we have a blurry training views, and we perform single image deblurring to each training image, and we obtain deblurred training views like this, and then we use these deblurred results to reconstruct the radiance field, and then we can render sharp novel views. But this naive approach does not really work well, which is in fact already shown by the authors of DeepNerf in their paper. And so here we have an example. So this is the result of the naive combination. So as you can see here, the rendered novel images, this rendered novel image still have some distortions and some degradations, and the details are not really accurately restored, and it still has some remaining blur. And this is due to the limited performance of single image deblurring. So while single image deblurring has been extensively studied, it is still a very challenging problem, and even recent state-of-the-art methods often fail to accurately remove blur. So because of the poor quality of deblurring results, this naive combination fails to reconstruct a sharp and clean radiance field, and as a result, novel view rendering also produces degraded images with the remaining blur as shown here. So to overcome these limitations of DeepNerf and its variants, and also overcome the limitation of the naive combination of DNN-based deblurring and radiance field reconstruction, we recently developed a new approach called Deep Deblur RF, which we presented at CVPR this year. And our method is the first approach that adopts pre-trained DNNs for deblurring radiance fields. And thanks to that, it performs really quickly, and it is able to produce really high quality results. And it is also very robust to real world degradations. So the key idea of deep deblur RF is like this. So here we have a blurry input, and we can apply single image deblurring. And as I said, single image deblurring has limited performance. So so as a result, the deblurring result is not of really high quality. So as you can see here, this deblurred result looks sharper than this blurry image, but it still has some remaining blur here, and it has some it has some high frequency information that is lost. Okay. But fortunately, we have multiple input images as we are constructing radiance field, right? So we have multiple blurry images, so we have multiple deblurring results like this from multiple views, and then we reconstruct the radiance field, and this radiance field reconstruction basically aggregates complementary information from multiple views. So thanks to that, even if one image, one deblurring result may have some degraded information. That degraded information may be restored by some complementary information from other views. Okay, so thanks to that, if we render a new image for the same viewpoint of this blurry input, then this rendering result actually exhibit improved quality as shown here. So as you can see here, this rendering result has more high frequency details compared to this initial deblurring result. Okay, so um, so based on this observation, our key idea is like this: we can use this rendering result as some kind of a guidance to remove blur, to more effectively remove blur from this blurry image. Okay, so this one provides us some hints about what the sharp image would look like. So we may use this image as a guidance. Okay, so we train image deep learning network to take these images, these two images together, and to produce a deep learning result for this blurring input. So we call this step RF guided deep learning or radiance field guided deep learning. Okay? And then thanks to this guidance, we can more accurately restore high frequency details from this blurry input as shown here. So as you can see here, this deep learning result has higher quality details compared to this rendering result. Okay, so we can actually repeat this process again and again, and we can progressively improve the deep learning quality. So based on this idea, we construct a pipeline like this as an alternating framework. So uh, So this figure describes the overall pipeline of our method. So we have blurry training views, and to each of the blurry training views, we apply a single image deblurring. So which we call initial deblurring. So after this step, we have multiple deblurred results, and then we construct a radiance field using these deblurred results, and then we render guide images like this. And then for each blurry training view, we concatenate that with each corresponding rendering result, and then we deblur the blurry training views again using this RF guided deep learning network. And this one had higher quality information, and then we use these deblurred images again to reconstruct the radiance field, and we repeat this process a few times. So in our implementation, we repeat this process like 4 or 5 times, and then we found that 4 or 5 iteration is enough. And so also for this radiance field reconstruction step, we can actually adopt any representations. For example, we can use NURF or Prenoxel or 3D Gaussian splatting. Okay? So as the iteration goes, the quality of the novel synthesis improves like this. So this one is the result after the first iteration. So this one is the rendering result after the first iteration. So as you can see here, the high frequency detail is restored somewhat, And after the second iteration, we have higher quality details. And after the third iteration, we have even higher details like this. And after the fourth iteration, we have really high quality details like this. And as you can see here, the PSNR increases as well as the iteration goes. And in our framework, we actually have this RF-guided deep learning network. This is a neural network. So we have to train this neural network. So to train this neural network, we also proposed data set. So we proposed a synthetic data set, which is called Blur RF Synth data set. And we released this data set on our project webpage. And also we released a real data set, which is called Blur RF data set, a Blur RF real data set. And this data set is for evaluation. So, and we also released this data set on our project webpage. And this data set provides low light images with severe blur and severe noise and other outliers. And we are here. This slide shows the quantitative evaluation result. So the x-axis describes the training time, and this is a log scale. So, and this here this is faster and this is slower, and we have the y-axis describes the PSNR values or image quality of the novel synthesis, and these are all previous methods, and these methods are marked in star. These two methods correspond to our method, and Deep Blur RFP is the Planexor version of our method, and Deep Blur RFG is the Gaussian splitting version, 3D Gaussian splitting version of our method. So as you can see here, our method achieves highest quality results within really small training time compared to previous methods. And here we have some qualitative comparison. So on the left, we have a blurry input image. And as you can see here, we have severe blur and severe noise, and also saturated pixels here, which are actually outliers that cannot be modeled by traditional grammars. And on the right, we have deep blur RF. We have a result of the of our approach. So as you can see here, our approach can successfully restore high frequency details. And we have another comparison, and on the left, we have a result of XBLURF, and this is another variant of deep blur RF, deep blur NERF. And as this XBLURF also relies on linear blur model, it cannot effectively handle severe noise. Okay, but so the rendering result has a lot of remaining noise and distortions like this. But unlike this result, Deep Blur RFP, which is our method, produces really clean, sharp result like this. And yeah, here we have another comparison, and on the right, this is a result of deep learning 3D-GS, which is presented at ECCV last year, and as the input image has a severe amount of noise, this one also fails to reconstruct a really sharp, high-quality radiance field. But in contrast, our method can reconstruct a high-quality, sharp radiance field while effectively suppressing noise. And even though I only described the motion blur caused by camera shake, we can actually apply our method for defocus blur too, because we can just simply train our networks for defocus blur. Okay. So this example describes that. So here, this image shows severe defocus blur on the background, and we can even with images with severe diffuse blur, we can reconstruct we can reconstruct a sharp radiance field while effectively removing diffuse blur. So to summarize, we in this work we presented the first RF deep learning approach that leverages DNN-based deep learning, and thanks to DNN-based approach, our method is effective, can effectively handle real-world images, and it is also computationally efficient. And on the other hand, our method has a couple of limitations. Our method may fail when the input images have severe blur than those in the training data, and I guess I have limited time, so let me just skip this part. So let me conclude the talk. So in low light conditions, it is really important to effectively handle noise and blur to reconstruct a sharp, high-quality radiance fields. And several works have been proposed for handling noise and blur, but especially for blur, and most of them rely on multiple rate sampling for blur modeling, which is very similar to classical image deep learning approaches before deep learning. And because of that, they share similar limitations to traditional deep learning approaches. And to overcome these limitations, we developed the deep deep blur RF, which is based on DNN. And thanks to the effectiveness of DNN-based approach, our method can also produce high-quality radiance fields, even for images with severe blur and severe noise and severe outlier. Okay. Yeah, and that's it for my talk. And
Thank you